use the limit comparison test to do it. So you can look on your little table if you need to, limit comparison. What we're doing is taking the limit as n goes to infinity of which one over which one? This one is called a sub n, this one is called b sub n. Which one goes on top? A sub n. So I take this one up here, 1 over n squared plus 1 over 1 over n squared. What am I hoping for? That this limit is a what? What does limit comparison say? What? A positive constant. Any positive constant. If this turns out to be a positive constant, what's the result of the test? Whatever this one did, this one does. So I'm just hoping for a positive constant here. It's going to happen. Right? Just flip the fraction before you do anything, all right? Just flip it. That's why I recommended we do it. Flip it, it's n squared over n squared plus 1. Right? That's what that is. L'Hopital, 1. Positive constant. Therefore, that sum 1 over n squared plus 1 converges. Which means what in the grand scheme of this problem? We do want 5/3 to be in our answer, right? So finally now, can you tell me for what values of x the original problem converged? So this series, n equals 1 to infinity of 3x minus 4 to the n over n squared plus 1 converges on the interval 1 5/3 inclusive, which is why I have brackets on both. That's using what we've already learned, right? Now, I wonder if we could, like in these problems, I wonder, and maybe you should wonder the same thing, that if one endpoint works, the other one must also work. Like you only have to check one. No. It could happen that one works and the other doesn't. Or that they both don't work. Or this one works and that one doesn't. Or they both work. So you have to check each endpoint.
The main reason I guess it matters is because if we're displaying an interval notation, we have to check both, otherwise the interval notation will be incorrect.
Yeah, if you were to have never done any checking and you put this as your answer, you never check the endpoints, this would be incorrect. Because you're telling me I can't plug 1 in, but you can. Or 5/3, but I can. Now you could get lucky, and that when you checked it, it didn't work, and get lucky, but I'm going to be looking for the work. So. All right. Are you kind of seeing a little bit of why we went through these convergence tests so that we could deal with the power series endpoints? Okay. All right. Next example, which is called an order 0. That's a 0, not an O. Bessel function. Now, Bessel functions are used in many different areas of engineering, physics. Let's see, they might even have something in here about it. Yeah, I'll read this here. Power series are used to represent some of the most important functions that arise in mathematics, physics, and chemistry. In particular, the sum of the power series in the next example, which is this one I'm about to do, is called the Bessel function, after the German astronomer Friedrich Bessel. He only lived 1784 to 1846. And these Bessel functions helped Kepler solve his planetary motion equations. These are used in different physical situations such as temperature distribution on a circular plate and the shape of a vibrating drum. So if you were to graph this function, it would be very good at modeling what the top membrane of a drum looks like as it's vibrating after it's been struck. You can model it with a Bessel function. Anyways, we want to know if this is a power series, what is the domain of this function? Okay, so we write it like this. Find the domain of this function. Capital J sub 0. This tells you it's the 0 order Bessel function. There is a first order and a second order. In fact, I will give you, as a homework problem, to find the domain of the first order Bessel function, which is a little different than this one. So here's how we're defining the function. J sub 0 of x equals summation n equals 0 to infinity of -1 to the n x to the 2n over, 2 to the 2n times n factorial squared. I don't think we've ever seen that much crap in one problem, like that much stuff mixed up, right? All right, let's go to the ratio test, all right? And hope that things get nice. Ratio. Do you all understand that asking what the domain of this function is the same question as asking for what values of x does this series converge? Yes? Same exact question? All right, so I'm gonna take this, I'm gonna plug n plus 1 in for everything first. So -1 to the n plus 1, and then, Yeah.
Can you combine?
I think I'm gonna take this one really slow, okay? X to the 2n plus 1 over 2 to the 2n plus 1, and then n plus 1 factorial, but then squared. So that's kind of messy. You have to be real careful how you put these n plus 1s in. N plus 1 there, 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 and there. Did I see a hand? Questions? I'm not done, right? I need now to divide this by this, just like that. So flip it and multiply. So I'm going to have times, on the bottom was 2 to the 2n times n factorial squared over the top, which was -1 to the n times x to the 2n. I want this to be what? Less than 1. That looks like a mess, doesn't it? So let me start with the easiest thing. These don't matter. Bless you, right? Because the absolute value of -1, no matter what this number turns out to be, when I take an absolute value, it's going to go back to 1, isn't it? Same with on the bottom. So those you never even have to consider, which is good. Cancellation, though. This is what I'm hoping for, right? Lots of cancellation. So let's take our time to split these up. And I'll do these maybe over here so we can see them. How about that x to the 2n plus 1? Isn't that x to the 2n plus 2? And that's x to the 2n times x squared. Agreed? Yes? So I'm going to rewrite that right here. Limit. N goes to infinity. This top is x to the 2n times x squared over, how about this 2 to the 2n plus 1? That I could rewrite as 2 to the 2n plus what? 2, which is 2 to the 2n times 2 to the 2. So this is 2 to the 2n times 2 to the 2. Questions? where's it? Yeah, we could write that as 4. I just want to make sure everyone sees where it comes from. This one, let's be real careful with this. N plus 1 factorial squared. This is n plus 1 times n factorial, right? That's what the inside is. But then squared. And when you have two things being multiplied and squared, can't you split it up into two different things being squared? Right? X times y squared equals x squared times y squared. You can do that when there's multiplication. So I'm going to rewrite this as n plus 1 squared times n factorial squared. See it? So n plus 1 squared times n factorial squared. And now I'm hoping that that's enough cleaning up to get things to cancel. What was still over here was 2 to the 2n, n factorial squared, and x to the 2n down here. I need to put that less than 1, but does everyone have this part down? May I want to hold it for a second? Or, no? I don't know if the ibuprofen kicked in or it's just some power series medicine. I feel much better now. I wish I could go faster. I mean, I'm not in a race to try and finish this. I know we're going to come up short in this class and not finish what we were supposed to, but I just don't want to rush through this. I mean, there's a lot of little things in here, and I think we've done good so far. All right, this is gone. 2 to the 2n's gone. N factorial squared is gone. That's pretty damn good cleaning up right there, right? Yeah, I'm pretty happy with that. So now I'm going to collect everything that has n together and everything that has x together. So this will be the limit. N goes to infinity. All right, what's left n-wise? Nothing on top? Oh, that's wonderful. On the bottom? 4 and then n plus 1 squared? 2 to the 2. So 4 n plus 1 squared. Why am I excited? Good, what? That's going to go to 0, isn't it? So it's not going to matter now what x turns out to be. Yes?
Why did you put 4 with the n term, not the x term?
2 to the 2 next to
Oh, I see what you're saying. In this problem, it's not going to matter because it's going to go to 0. But let's just say this would have gone to 1. Then that 4 would have come into play because it would have been 1/4. Now, if you would have put the 1/4 over here, then this would have gone to 1, and then it still would have been 1/4. So it would have stayed in there no matter where you put that constant. That's a good question. It doesn't matter. With constants, you can put it on the left or the right. Nope. Nope. All right, so that's that. What was the x that was left here? X squared, and then less than 1. And that goes to 0 times x, and that's always less than 1, x squared. That's always true. So what's the domain? All real numbers, right? So that means the Bessel function of order 0 is defined everywhere. For every real number, the Bessel function is defined.
So like with these kind of questions, where it's everything, you don't need to check the n.
That's right, because you can't, right? You can't check infinity. All right. So let me see here. Man, I haven't given you this one particular example. Shit, I'm running out of time. All right, let's look at another one real quick. I'm going to do this one quickly. And I'm going to do this there we go. Sum n equals 1 to infinity. This is not on your sheet. Of n squared x to the n. You ready? I'm going to move quick. Ratio test. Same question, right? For what values of x does this converge? I've read ration. I don't know why I love writing ration. Ratio. So limit n goes to infinity. Absolute value. Plug in n plus 1. N plus 1 squared times x to the n times x. Because this wasn't a fraction to begin with, I'm not going to do that flipping thing, right? I'm just going to do that and then divide it by that, right? Oh, crap. It's not what I wanted. Damn it, that's not what I wanted. Shoot. This isn't going to do what I wanted it to do. Because what's this going to go to? Infinity over infinity, when you do L'Hopital, it's going to be 1. So it's going to be absolute value of x less than 1, right? Okay, scrap it. I wanted to do something in particular. I should have changed it. All right. Make it n to the n. Pardon? N to the n, all right? N to the n. So we could use ratio test, right? This is actually number 10 out of the homework. I already did number 10. It's on video. It's on YouTube. You can I'll show you. If you watch that video, I do it a certain way. And then after I do it a certain way, I come back and I show you how to do it a different way. I'm going to show you the second better way to do this. Instead of using the ratio test, use the root test. Why would I use a root test? They're both raised to the n power, right? What does the root test tell us? Limit n goes to infinity. The nth root of what's in there, that if that's less than 1, it converges. If it's greater than 1, it diverges. And why is that root test useful there? What's going to happen here? This is n times x to the n, isn't it? That's what this is? And then this n and this nth root go away, which leaves you with the limit as n goes to infinity of what? What's there still? N times x? I need that to be less than 1. What's wrong with that? N goes to infinity. Right? But you can't control x, right? So look, you come in, you fix an x, and then I let n go to infinity. Is there any way that you can make that less than 1?
Negative 0? Making it negative 1?
Only if I choose x to be what? 0. Right? If I choose x to be 0, do you agree that this will converge? But any other choice of x, and it's game over, isn't it? If I let x be 1, that goes to infinity. I can't keep it smaller than 1, can I?
Negative 1.
It's going to be infinite, right? Well, this is, I left the absolute value off. It's absolute value in here. Yeah, sorry. There's absolute, ooh, sorry. I should not have left that off.
I was going to say like that.
That would have made a difference. Yes, I hear you.
Infinitely less than 1.
Yes, you're right. Negative infinity is less than 1. Yeah, if you go back and look at the root test, this has an absolute value on it.
Okay.
So the only way this is ever going to happen, only if x is 0, right? And that's the only answer. That's your domain. One number. This is a function that is defined at one number. Big deal, right? Not a very interesting function. But we kind of knew this to begin with, didn't we? I mean, didn't we say earlier that if this is a power series about, here it would be about what? About 0? Isn't this a power series about 0? Then if I plug 0 in, shouldn't I get it to converge? Yes?
Yeah, but now it proves that it's only 0.
That's only 0. Only if x is 0. So how would we say the domain, like if this was a function?
0 to 0.
We use a set of braces. Intervals are parentheses and brackets because they include everything in between. If you're only talking about a single number, you put a set of braces around the number. So it's the set of numbers that just has the number 0 in it. All right, now this leads us to the theorem. This is the big theorem, the big result. All right, so please look on your notes. It's on the page, says theorem. Given a power series, any power series, there are only 3 possible results that you could get in terms of its convergence. All right? There's only 3 different things that could happen. First, it converges only when x is a. That was the problem I just showed you. Right? The example I just showed you, it only converged at one value. Right? That's going to happen. Or the second possibility is that it converges for all x, which means that negative infinity to infinity is where the domain is, or where the interval of convergence is, right? So it's either at a single point, an interval. Now this interval might be, the entire number line. I'm getting myself ahead of myself, sorry. It's either going to converge at a single point or on the entire number line, or finally, the only third option is that it converges on an interval. And that interval might be, I say this on the bottom, might be closed on both ends, closed and open, open and closed, open and open. It could be any of those 4 possibilities. Okay? That's it. That's the theorem. This means that it is impossible for a power series to be defined on 2 different intervals. So you remember how we were talking about, like, if you graph that very first one we did, we said if we graph it, it would be between -1 and 1 would be the graph. It's impossible for a power series to have a graph where the graph is somewhere over here, and then it's missing piece, and then it's somewhere over here also. It has to either be only defined at one point, defined everywhere, or on some single interval. And that's it. And because of this, we have this terminology that we use, which is called the radius of convergence. The radius of convergence. So let's look at these situations right here. Let's say that I tell you that a power series converges everywhere. What would that look like? If I were to say a power series converges on negative infinity to infinity, on a number line, that would be in both directions forever, right? Yes? So when we look at the distance in that direction and that direction, if we call that distance r, how big is that radius? So look at the zeros, the center, and look out both directions. How far is that distance out? Infinity, right? We would say the radius of convergence would be infinite. Capital R is called the radius of convergence. This is in the notes. What if we have, that's one scenario we could have. What if it converges on some interval a, b? So A, B. What would its radius of convergence be? We don't know if it's 0, though. We don't know if it's centered there, right? Because it could have been moved over. The distance from here to here would be r, and the distance from here to here would be r. All right? You could go try and figure it out, but let me show you where the easiest way to find it, okay? When you're working through your power series, that's supposed to be x minus a to the n. The x minus a part in absolute value is less than capital R. This is where the capital R comes from. Now, you'll have to work for it. We'll see in a second. We're going to have to work for the capital R. But this is where it'll come from this inequality. This inequality is going to come from the ratio test usually. And it's usually going to be less than 1. But we'll just have to work through some for now. Do you see it visually? Here, does it make sense that you have an infinite radius? Here, does it make sense that you have a finite radius? And what's the last possibility for a power series? A single point. What do you think the radius of convergence is at a single point? If I tell you, boom, right there, that's the only place the series converges.
That's the domain.
That's the domain, 1 point. Then what do you think your radius is? What's the distance?
0.
0, right? You can't have a radius at a single point. So your radius of convergence would be 0. All right, I have 15 minutes. Let's see what I can do in 15 minutes. I think I've got a couple of more examples on the back. So look at the last example, or these last 3 examples, and take a look at what they're asking. Find the radius of convergence and the interval of convergence for sum n equals 1 to infinity, 1/4 to the n, x minus 3 to the n over n root n. So they want us to find 2 things. I'm going to call them r for the radius of convergence and I for the interval of convergence. These are 2 different concepts. The radius is how wide the interval is, and the interval of convergence is the actual interval, which is what we've been doing. We've been finding this, right? Yeah? All right, so how do we find where that converges? Ratio test? Ratio? Limit. N goes to infinity. You getting tired of it yet? Negative 1/4 to the n plus 1, but I'm going to split it now. All over n plus 1 times root n plus 1. Ooh, not looking forward to that. Is that me plugging n plus 1 into everything? Okay. Now, multiply by reciprocal of that thing. So n root n, and then 1/4 to the n x minus 3 to the n. I need that to be less than 1 for it to converge. I know right now you might be thinking, oh, okay, our radius of convergence is 1 because this is going to be that absolute value thing. But just hang tight. Let's see if that actually happens. I can cancel now, right? I forgot a negative right here. Everyone see that? Yeah, I had it. This is gone. I don't see anything else gone, do you? No? So let me rewrite this now. Limit n goes to infinity. All right. What do we still have here? Do you want me to put the negative 1/4 here on top? Okay with you? N root n over on the bottom.
You can put it together.
What, these two? Yeah, you could. You could. I'm not going to, but not because I can't. It's just, we'll see on the next step. That's all my n stuff, right? Times, what's still here? X minus 3, right? That's all one factor, so I put the whole thing in parentheses. Did I miss anything? It's good? So what do I need to determine now? What all this stuff goes to, right? As n goes to infinity? So watch the way I write this. Limit n goes to infinity, negative 1/4. Well, let me just for the sake of doing it, n over n plus 1 times root n over root n plus 1 times negative 1/4 times x minus 3 there. Just, do you agree or not? Is that the same thing? I just slid the negative 1/4 way out here. I'm doing this over this, this over this. Anybody have an idea of what I'm about to do with this? We did it, I think, last class. Just put the square on the whole thing, right? So that would be legal for me to do, right? To just do a square root on the whole thing. And now I'm going to see what happens when n goes to infinity. What does this piece go to? Right here. Okay, so L'Hopital on that would go to what? 1? That goes to 1. Times L'Hopital on the inside of that. 1. Square root of 1 is 1. So that goes to 1 also, right? That's a lot less work than trying to do a bunch of other stuff. You could try and multiply this out and do L'Hopital's rule, but I mean, just imagine L'Hopital's rule on this. It wouldn't be fun, would it? Like derivative of the bottom would be product rule. And so I can do away with the limit now. So now I have absolute value, negative 1/4 times x minus 3 less than 1. Now I just showed you a second ago that to get your capital R, you need to get it to look like this. Capital R will be the number that's over here after you've got the x minus a by itself. So I have a problem. I have the negative 1/4 there. So I'm going to break this up into two absolute values like this, because that's the same thing. And what is the absolute value of negative 1/4? 1/4. So this is 1/4 times the absolute value of x minus 3. And now finally, to get the absolute value of x minus a by itself, multiply both sides by 4. Okay. Does this look like this now? Yes? So what's our radius of convergence? 4. Our radius of convergence is 4. Bless you. Now, what's the interval of convergence? That's a different question, right? Now what I have to do is take this and drop the absolute value, which means it turns into x minus 3 less than 4, but also greater than negative 4, right? Can you now solve for x in the middle, like get x in the middle by itself? Negative 1.
Now we check the endpoint.
Now check the endpoints. Yeah, so I still have 7 minutes, so I'm going to check the endpoints now. But I'm going to go real fast with these endpoints. You're good? All right, you ready to check the endpoints? See, I know how wide the interval of convergence is, right? I know the radius. I know that whatever my interval is, right, what, -1 and 7, I know that what's right in the middle there? 3 is right in the middle. What's the distance from here to here? What's the distance from here to here? 4. So the radius of convergence is the distance from the center out in each direction. The question is, do we include the endpoint or not? What's that? Okay. All right, so what do you want me to check first? You want me to go with -1 first? Okay, let x be -1. I've forgotten what the series is. N is 1 to infinity. I had -1/4 to the n, and then I had x minus 3. So -1 minus 3 to the n, and then over n root n, right? That was it? But this is just, what, -1/4 to the n times -4 to the n over n root n? Yeah, what do those do? They come together because they're both to the n power and become a what? A 1, right? -1/4 times -4 is +1 to the n power. So it's really just 1 over n to the 3/2. I finally put it together for you. Why'd I do that? Right, when you put those two together, you get n to the 3/2. That's a p series. P is what? Which means converges. So I want to include -1, don't I? Isn't this fun?
No.
No, okay. I thought you said, oh. I thought you were like, oh, yeah. All right, so we do include that endpoint. The other one we have to check? 7. So how's that going to change things? Not much. It's not going to be a nice 1 up there anymore, though. Watch, if I change this to a 7, this is no longer a -4. It's now a +4. So how does that change this next piece? It's -1 to the n. And then over, you could still do n to the 3/2, but you can't say it's a p series, right? But you can say it's an alternating series, and then you can go through the test however you want to do it. I'll do an alternating series test check real quick. I'm going to use this piece right here. B sub n is 1 over n to the 3/2, right? I'm going to use alternating series test. What are the two things I have to show? Decreasing, and the limit of that goes to 0. Does the limit of that go to 0? Yeah, I'm going to do that just by visual inspection, right? We all agree, yeah? That goes to 0 as n goes to infinity. So let's just show the decreasing part. How do you want to show the decreasing part? You want me to set up the inequality? Yeah? I don't feel like it, though. Here's what I'm going to do instead. I'm going to look at this as a function of x and call it x to the -3/2. And then what am I going to do? I'm trying to show you that this is decreasing, right? Take the derivative and show you that it's what? Negative. Negative, right? So here's this rewritten as a function of x. If I take the derivative quickly, because I have 2 minutes, I get negative 3 halves x to the derivative, not antiderivative. Negative 5 halves? Yes? And this is really, let's see, negative 3 over 2x to the 5th square root. That's what that means. And if you're plugging in values of x that are bigger than or equal to 1, do you agree that the bottom is positive? That's always positive? And that right there is negative? And so this ratio is always less than 0, which shows it's decreasing. You could have done it with the inequality. I was just having fun with the derivative. Right? Either way. So what do we conclude? Does the alternating series both checked off, right? So it converges, right? So both endpoints. So my final result is the interval of convergence is -1, 7, including both endpoints. Bam. We're done. We still had 2 examples I didn't do. I have done the homework problems out of this set up to number 11. I ran out of time. I don't know when I'm going to get to 13 or 12 through the rest. Hopefully tomorrow. My plan is to come in tomorrow morning and knock those out. But you can at least do the first 11, and you should try the rest. I'm going to put the assignment up here for you. And to think I thought we would get through 1.5 sections today. I thought we'd start the next section. So we don't meet again until Tuesday, right? And then Thursday, and that's it. We're done. And we have, I would like to cover 2 more sections. So 1 per day, hopefully. Page 468, your homework for this. I would go and do 3 through 22. Well, that's what I'm going to do. I'm going to do 3 through 22. I'm not sure what you're going to do. At least up through 16, okay? 3 through 16 would be, the minimum. Once they get past 16, they get pretty weird. And then also number 29. It's an odd. I can't offer it as a bonus. 29 is the first order Bessel function to find just part A. Part A. All right, have a great Thanksgiving and great holiday, safe holiday. I'm going to come in on Thursday anyway if anyone wants to come. No, I'm kidding with you. I think campus is closed.